Good morning. You probably ask why I ask you to scan that, but everything will be revealed later on, so don't worry. Good morning. All yours. Good morning. Good morning. Good morning.
Morning.
Good morning. Good morning. Right, let's make a start. Most wonderful good morning, everybody. And welcome to our last but one session for the data analysis. People have asked me about the assessment, and it looks like there are weird things going on the Moodle page. I can assure you that, to my knowledge, and that is Thursday, the 3rd, is it the 3rd? Yeah, 4th, whatever, 3rd, of November, 11 o'clock. It is a data analysis task that you do in your assessment, and not the grant proposal or the pre-proposal. Despite whatever it says on the Moodle page, I will need to check that. I will open the assessment when you are ready. You're not ready yet, because we need the session in week 16 for you to complete the assessment and get everything done. So, okay, please don't forget to register your attendance. I hope the Moodle code works. Does it work? Thank God for that. because I'm always paranoid. My stage 1 students, twice I gave them the wrong code, and it was a sort of almost a riot. Okay, so what I want to do with you today is I want to show you how we can actually determine confidence intervals. And just a recap from the session last week, we said confidence intervals depend on a number of factors. So confidence interval depends on the variability. Yeah, that was the wrong one. They depend on the variability in the population. And as a sort of a reminder, why do we want to use confidence intervals? Well, because we just simply said, if we take a sample and we want to make an inference on the population, it doesn't really make a lot of sense to give a just simple point estimate. Instead, it makes far more sense to say, well, the height of the students in the population, the average height is 177 centimeter plus minus, say, 12 centimeter or something like that. And that would be the confidence interval, this plus minus. It makes far more sense because every time we take a sample, we might come up with a slightly different value for the estimated average. This is the nature of sampling error. I told you sampling error is just simply that is what you have. We can't do anything about it. And therefore, we, instead of saying it's that exact value, we are a little bit more careful and say we give it a sort of a wiggle room. That is the confidence. So it depends on the variability in the population. Usually we don't know that, so we have to estimate it from our sample. Which is a little bit annoying, but we don't have this information. We also said that the confidence interval depends on the sample size. The bigger my sample size, the more information, in a way, do I have already about the population. And therefore, my sort of uncertainty would be smaller. Higher sample size, smaller confidence interval. Large variability, I have to use a very large confidence. The third factor that I told you is my sort of preparedness to make a mistake. So that would be the significance level. Or the confidence level. And I told you, I gave you this example with the bouncer and the airline lounge. How prepared are we actually to make a wrong decision? So when we get a confidence interval and we say, according to our sample, we say it's 177 centimeters plus minus, say, 10 centimeters. That's our confidence interval. So it will go from 167 to 187. But that is just an estimate. How willing are we to have this estimate wrong in a way? And this also determines the size of the confidence interval. So basically what we are looking at here is what error are we willing to accept? That the bouncer, for example, rejects us despite we are being in the right place. So the significance level you find that very often abbreviated as alpha. This is also known as the type 1 error. And there is a nice relationship between the significance level and the confidence level. This relationship is basically the significance level alpha plus the confidence level which is basically the opposite of alpha, always add up to 100%. So what does that mean? If I say I want to determine a 95% confidence interval, and that is actually very common, 95%. It basically means we want to be 95% of the time right in our estimate for this confidence interval. And we can immediately calculate alpha because 95% confidence interval means 1 minus 95% equals 5% for our type 1 error. So alpha plus confidence interval always adds up to 100%. Why is it 5% or 95%? Well, it's just one of these things that, in social sciences, people prefer, an error of 5%. Very often in the hardcore sciences, people go for an alpha of 1%. You can set it whatever you want. Set it, this error margin, set it to small, set it to 0.0001%. You don't want to make an error. That means your confidence interval will be huge. Will be basically you saying, if I measure the height of people and I don't want any mistakes in it, I say they will be from 0 centimeter height to 5 kilometer height. I can guarantee you that you will be 100% right and your alpha will be basically 0. But what do you do with this information? It's nonsense, right? Just as well don't do it. On the other hand, if you set it too small, if you say, from my sample, I estimate that the confidence interval is between 176 and 178, you will find that when you do a lot of measurements, most of these measurements are totally out, are not within this confidence interval. So again, set it too small, you don't get any decent values. So 5% seems to be sort of a bit like the Goldilocks, the not too hot, not too cold thing, and people very often go for 5%. And I also told you, and that is basically what we are going to do today, that the last factor that we need to do for confidence intervals is they depend on the data type. Strictly. And you can't mix and match. You have to say what type of data you have. And we will look at 3 data types. We will look at count data. We will look at proportion. And we will look at continuous data. Okay, so how do we find confidence intervals? Let's look at a confidence interval for count data. The good thing is you don't have to learn any equations, because the calculations can be a little bit, shall I say, involved. How do you find them? You find them with this online calculator, for which you have got the QR code, and I will post that on Moodle and also send it around in a Moodle announcement. It's a great online calculator, but you need to know actually how to operate it. So, someone wants to scan it. Bookmark that page. You will need it for your assessment. You'll definitely need it. Okay, so count data. Let's assume we have a petri dish and we have some colonies on it. In this case, we can count the number of colonies. 1, 2, 3, 4, 5, 6, 7. 7 colonies. And we treat this as a sample. And I want to know how many colonies would I expect if I repeated the experiment loads and loads of times. How many colonies per plate would there be? Now I could say, okay, I would expect 7 colonies. But again, this is the thing with the sampling error. If I repeated that, it could be 8 or 10 or something like that. So I need to figure out how I can do the confidence interval for that. And what we can do is we can use this online calculator. I'll show you how to use that. So if you scan, you probably come to a page like that. Those of you who have scanned it, do you get to a page like that? Yep. And this is actually the calculator that does all the hard lifting for you. Now you need to make sure that you are in the correct tab. You see, we are dealing with count data, so that's the most right-hand side tab, count data. I need this part here at the moment. Let me just quickly get rid of that. And we said we have 7 colonies. 7 colonies on a single plate. And it says here events and days. This is just simply because this calculator is used for some other purposes, but it does exactly the right calculations. We will come back to that in a moment. And what it will do, it will spit out confidence interval, a 95% confidence interval. If you want to change that, you can do with the slider down here. But it basically tells us it is between 2.8 colonies and 14.4 colonies that we would expect in the long run. This is how this what this calculator tells us, it gives us the confidence interval we would expect between 2.8 and 14.4 colonies if we repeat. In a way, this would be the colony count for an infinite amount of plates. So let's write that down. So the confidence interval is between 2.8 and 14.4. What if, for example, we have 3 plates? One we have 3 on it, and the other one we have 10. So we've got 7, 3, and 10. We could calculate a mean for that, but the way you calculate confidence interval is you say you've got 3 plates, you just add up all the counts. So in this case, that would be 20, am I right? So the sum is 20, and we have that on 3 plates. So for our calculator, we would put in 20 colonies on 3 plates, and we get a confidence interval of 4.1 to 10.3. Make sense? How this is calculated, don't worry too much. We would have to go into a lot of, distributions and things like that, and I don't think it is worth discussing it. This is for count data. Now, under which conditions does this apply? This type of count data calculation. There are some restrictions. The distribution, statistical distribution for the experts, this is called a Poisson distribution. If you want to read up on that. And it basically works with count data in a defined space or time. So define space here on plates or time when we look at how many events actually happen in a certain time frame. This is when a Poisson distribution might be applicable. And the restrictions are the events must be independent from each other. So a colony must be independent from the colony next to it. 2 events at the same time or space can't happen. There must be single events. And the probability for an event to happen must be equal in the entire space or time. Let me give you an example about that. If I want to figure out how many people on average in the long run are using the toilet in a pub, that would usually follow a Poisson distribution. So what I do is I just sit outside the toilet and say in an hour or so, I count how many people are going to the toilet. That would be a nice Poisson. Time and count data. Doesn't work always, because if I, for example, sit down in the morning when the pub is closed, and then compare that with Friday night at 10 p.m., it doesn't work, because the probabilities are not the same. In the morning, nobody goes to the toilet because it's closed. In the evening, everybody goes to the toilet. So that would be a violation of the Poisson distribution. I could not compare these data with each other. Another thing is that you probably have observed. Usually, that is a sweeping generalization, but I am happy to hazard a guess here. Very often you will find that ladies turn up in packs, right? It is, you want to come to the toilet with me. And then they come in, you know, sort of, I don't know, a gaggle or whatever it is called. So they are not independent of each other. Obviously, they are not, you know, doing any biological thing. They're talking about, you know, important things. On the other hand, so with ladies, you could not do that because they are not independent of each other, and they can come, you know, at the same time. With guys, on the other hand, it's more likely that they follow a Poisson distribution, because, you know, if you say to your mate in the pub, "Shall we go to the toilet?" You might get some funny looks, right? So that's the Poisson distribution, and it's really easy to deal with. Okay, so for your CRISPR practical, you can actually count the colonies of your plates and say, what would I expect in the long run? How many colonies do I expect? Well, I've got a nice data analysis. You don't even have to do any calculations. Simple. Okay, let's look at the other one. Let's calculate a 95% confidence interval for a proportion or a ratio. Okay, let's say I've got 4 black colonies or white colonies and 2 red ones for whatever reason. So I can say the ratio so the proportion or ratio equals 2/4, right? No, actually, sorry, I need to write this in a different way. This would be not a ratio, this would be odds, but that's a bit odd. So we've got 2 red ones out of a total of 2 plus 4, which is 2 out of 6, right? So the ratio would be 1/3. But of course, could very well be that in the next experiment, it is 3 out of 7 or something like that. So again, I need to determine a confidence interval for that. What is the ratio in the long run? Again, we use our calculator, but this time we use a different one, because this is a distribution that follows a chi-square distribution, which is another distribution. So you want to click on the chi-square tab here. So we had 2 red ones, and the total number, so 2 successful events, if you like, and the total number was 6. So that's the total number of events. So that's 6. And it will give you a confidence interval, again, basically goes from 9.7% to 70%. It's huge. Write that down. 9.7% to 70%. That is our estimate that we get from this particular experiment. So the true percentage of red cells in the overall population is somewhere between 10 and 70%. I mean, that doesn't really help us a lot, does it? It's huge. Now, the ratio is very, very strongly dependent on the numbers, on the sample size. I'll show you. So we've got 2 out of 6. That gives us this huge confidence interval. Let's say, however, we do this experiment with huge numbers. Yeah. We can do that for the white colonies. We can do that 4 out of 6. That would give us the white colony. We can do that in a minute. I'll show you. Yeah. So we just do that with larger numbers, 200, and we have the same ratio, 200 out of 600. It's still 1 in 3, right? But now look at the confidence interval. What happened to the confidence interval? This confidence interval goes from 30 to 37% roughly. Much, much smaller because you've got larger numbers. Yep. Now, what you just mentioned, let's do that. Let's, in this case, look at the white colonies. So we would have 4 out of 6. And what you see is, if you like, the 70 and the 30 add up to 100, and the 97 and 90, 9.7 and the 90.3 add up to 100, right? So that's quite nice because you only have to calculate the stuff for 1. Make sense? This chi-square calculation, so that's a chi-square distribution, it gets a little bit iffy when you are very close to 0% or very close to 100%. Then it breaks down with your ratio. So if you've got 0 out of 10 colonies are red, be careful with the confidence interval because that's usually not terribly accurate. Or if you have 99 out of 100 colonies are red, then it's also be careful. And also, when you do a sort, this is very often used for surveys. So 8 out of 10 cats would prefer grilled mice, right? So you do a survey of the cats, but what you have to make sure is that the cats, that the size of your survey is less than 10% of the entire population that you're looking at. If it is more than 10%, might get away, but the numbers are getting a little bit shaky in this. In our case here, it doesn't matter because we could do the experiment 1,000,000 times And you know, we are small with one compared to a million. We are just, you know, we don't need to worry about that. So that was count and proportion. What about continuous data? 95% continuous data. Again, that's very easy if you know where to find it. On the calculator, you go basically to two-sample t-test, and that's something that we are discussing in the next session, where we can use that program there to calculate a 95% confidence interval. So let's go there. So count data. Let's say I measure the red color in some colonies that I picked. I measure absorbance in a spectrophotometer, and you've done the experiment. Oh no, you haven't done that yet. You will do that in the CRISPR practical. So for example, we take 3 cells and measure the concentration of the red color in it. So for the first one, we get 0.5. The second one, we get 0.6. And for the third one, we get 0.7. Let's do it like that. Okay, so these are count data, because there could be anything in between. These are continuous data, excuse me, because there could be anything in between. And now we can calculate the confidence interval for that, or we let the machine do it, the program do it. And it comes up with something that we recognize up here. It says it's 0.6. That's the mean of the data, actually. If you look at the data, we've got the mean here as 0.6, so it calculates the mean. And then it also calculates the range of the confidence. 0.6 plus minus 0.25, let's say. So here we had 0.5, 0.6, 0.7. Mean 0.6 plus minus 0.25, let's say. So here the confidence interval would go from 0.35 to 0.85. So minus 0.25 to plus 0.25. Have I done it right? Yes. Calculations. Good. And what you see is that the 0.6 sits bang in the middle. That is not always the case, because if you look at other distributions for the ratio distribution that we had here, it's also pretty much in the middle. But for the count data, it's not in the middle. That is just specific to these different distributions. What is the restriction actually for this distribution, and this follows actually a t distribution. The restriction for the t distribution is we can only realistically use it if it is continuous data. We can't use that for count data or ratios. And the sample that we have taken, our measurements, sample must come from a population that is normal distributed. What does that mean? Well, a normal distribution, you all have seen what a normal distribution is. If we, for example, plot the height of people, so height, and here the frequency, how often do we see that? What we will find is sort of a bell-shaped curve, right? You have seen these bell-shaped curves. It's also called a Gaussian curve or bell-shaped curve. And it has some particular properties, but I don't want to go too much into detail, which basically means most people are around the center, the mean population. There are a few people who are much taller, and there are also a few people who are much smaller. But in general, it follows this bell-shaped curve. And our population has to look like that. Of course, we don't know what the population looks like because, if I just pick a few people and measure their height, I get my continuous data, but I'm not entirely 100% sure that the entire population is, is normal distributed. I could have a population, for example, where I have either midgets or basketball players. Then it would be a bimodal distribution in the population, but I wouldn't know. So how do we know that the population actually comes from, that the population is normal distributed? You usually don't. But you can make an educated guess because the normal distribution is incredibly common. It would be very surprising if you had any other distributions for continuous data. But if you want, you can actually do a statistical test, which is called a Shapiro-Wilk test. And that will tell you actually whether your population is normal distributed. I think I've got a video on how to perform that. Again, it's an online calculator. You don't have to do the calculations by hand or yourself. And the Shapiro-Wilk test will tell you, yes, my data are normal distributed. If your data are not, if the data don't come from a normal distribution, most people will actually say, well, who cares, right? Who cares? We will still treat them as normal distributed population. The mistake that you make is probably not huge. And non-specialist would probably not recognize it. However, if you are dealing with sort of sticklers, they will say your data are, you have not proven that it is from a normal distributed population, so I don't trust your data. But there is a way around that I'm going to show you next week. So today, hopefully the take-home message is that you have learned how to use this online calculator, calculate 95% confidence intervals for the different data type, count data, which follow Poisson, proportion, which follow a chi-square, and continuous data, which follow a t-distribution. And you also understand under which conditions you can use these things, which basically means you are able to do the first part of the assessment, because you have to do exactly that. The second part of the assessment is where you have to compare confidence intervals with each other, which will bring us to week 16, where I show you how we do hypothesis testing and how do we compare two data sets, count data, proportion, and continuous data. Any questions? Oh my God, I'm so good. Thank you very much. Go in peace, but please go.